We have a new sequence of 9, 36, 144, 576, 2304. Let's identify the type of sequence. If we were to assume it was arithmetic, then the common difference would have to be the same. So let's see the difference between the two terms. 9 plus d would equal 36, therefore the difference between the two terms is 27. 36 plus d equals 24. The difference between those two terms is 108, and 144 and 576 difference is 432. They do not share the same common difference, and therefore it is not arithmetic. If we were to assume the sequence was geometric, then remember that we would need to find a number that we would multiply to each of the terms to get to the next term. So 9 times r would have to equal 36. The common ratio would then be 4, and it would need to be 4 throughout the terms. 36 times 4 gives you 144. 144 times 4 gives you 576. There is a common ratio, and therefore this is a geometric sequence. Now knowing that the sequence is geometric, we can identify the next three terms. And all we need to do is use a recursive process in which we take the prior term and multiply by 4. So what would be the prior term? 2304, because we multiply that by 4 to get the new term of 9,216. 9,216 now will be the prior term, which we multiply by 4 to get to 36,864. And we would do it one more time to come up with 147,456. In order to write the recursive formula for this geometric sequence, g sub 1, the first term, would have to equal 9, and g sub n, the successive terms, would have to equal 4, which is the common ratio, times g sub n minus 1, which represents the previous terms. When we write the explicit formula, we will take that first term, 9, and we'll take that common ratio, 4, and put it in g sub 1 and r respectively, and come up with the equation g sub n equals 9 times 4 raised to the n minus 1. As we try to figure out the 25th term of the sequence, which of the two formulas would make most sense? A formula that would be done recursively, where you have to find 24 terms before that point, or an explicit formula where we can jump to the 25th term directly. We'll use the explicit formula. We will go g sub 25, because that's what n is right now, equals 9 times 4, in which 4 is then raised to the 24th power. And that works out to approximately 2.53327 times 10 to the 15th. If I were to take the geometric sequence 9, 36, 144, 576, 2304 and continue it until I found a term number that equaled 37,748,736, what term number would that be? Using an explicit formula, I may not know what n is, but I do know that g sub of that n will be 37,748,736, which I can then equal to 9 times 4 raised to the n minus 1. Because you plan on solving for n, I would divide both sides by 9 first, coming up with 4,194,304 equaling 4 raised to the n minus 1. Now would be a good time to use a logarithm, and so you write it in logarithmic form, where you take the log of that number to base 4 and equaling to n minus 1. If we use the change of base theorem, we can then say that 11 equals n minus 1. So by adding 1 to both sides, we would figure out that 37,748,736 was the 12th term of the sequence. With the new sequence of 8, 21, 34, 47, and 60, we should identify the type of sequence we have. If we thought it was geometric, realize that 8 times a ratio would have to equal 21. If we worked out the ratio by going 21 divided by 8, we would get 21 divided by 8. This is not the same ratio if we would go 21 times r equals 34. That one would generate 34 21st as its ratio, just as 34 times r equaling 47 would produce a ratio of 47 34ths. Since there is no common ratio, this is not a geometric sequence. So if we assume it's arithmetic, 8 plus the common difference would equal 21. If the common difference is 13, that common difference needs to be consistent all the way through. And 21 plus 13 equals 34, and 31 plus 13 equals 47. Therefore, we did find that common difference, and we can establish that this is an arithmetic sequence. After identifying the sequence as arithmetic, we can now establish the next three terms by adding 13 to the prior term. This is the recursive process. 60 plus 13 would give you 73. 73 plus 13 would give you 86. 86 plus 13 would give you 99. The next three terms, 73, 86, and 99. The recursive formula for this arithmetic sequence will be written as the first term, a sub 1 to equal 8, and the successive or next terms, a sub n, will equal the prior term plus the common difference, or a sub n minus 1 plus 13. When writing the formula explicitly, substitute a sub 1 with 8, substitute the common difference d with 13, and write it as a sub n equals 8 plus the quantity n minus 1 times 13. If you wish to rewrite it more as a linear equation, then a sub n could equal 13 times n minus 5. If you wanted to find the 77th term of the sequence, definitely consider using the explicit formula, as all you need to do is substitute 77 in for n. You can do this in either one of the two formulas, and you'll come up with 996. If we continue on and we wanted to figure out what term 9472 was of this sequence, we would want to set up an explicit formula where 9472 equals the a sub n. That would equal 8 plus the quantity n minus 1 times 13. Again, I may not know what n is, but I do know that a sub of that n will equal 9472. I probably want to maybe, subtract 8 from both sides and then divide by 13 to come up with 728 to equal n minus 1. After adding 1, you come up with the 729th term. However, those that may have written the explicit formula as a linear equation and set 9472 to equal 13n minus 5, you would want to add 5 to both sides, divide by 13, and you'd still come up with the 729th term. Whichever method you choose will still work. Looking at this sequence of very large numbers, let's identify the type of sequence. Again, if we assume it was arithmetic, we would be able to take 1,129,900,996, add it by some difference, and we would come up with 484,243,284, which would give us a difference of negative 645,657,712. I am not going to keep saying all these numbers. You will just be able to realize that the difference is not the same throughout the process, and therefore it is not arithmetic. If we look at this sequence geometrically, we would need to realize that the first term would be multiplied by an r to get the second term. If we do a little division and realize that ugly number can be simplified to simply 3/7, and realize that that 3/7 is what's also used to go from the second term to the third term and the third term to the fourth term, that common ratio of 3/7 would tell us that we have a geometric sequence. If I were to take this geometric sequence and find its next three terms, I would use a recursive process in which I'd multiply the prior term by 3/7. And if our prior term in this case is 88,942,644, I'd multiply that by 3/7 to come up with 38,118,276. And I would continue on this process to find the next three terms. When I write its recursive formula, I would say G sub 1 equals 1,129,900,996. I would say G sub n equals 3/7 times G sub n minus 1. Explicitly, it would just be G sub n equals 1,129,900,996 times the 3/7 raised to the n minus 1. So when I figure out the 10th term, I would probably go explicitly, stick in 10 into the value, and I would realize that I would come up with a number of 551,124. And if I were to continue that sequence until I found a term that was 708,588 over 7 and wanted to know what term that was, I might set it up where that value equaled the explicit formula, or first term times 3/7 raised to the n minus 1, divide both sides by the first term, rewrite the problem as a log as I'm trying to solve for the exponent, and that would be the log of the fraction 708,588 over 7,909,306,972, all to base 3/7. That would equal n minus 1. Using the change of base theorem, I would then realize that 11 equaled n minus 1, and this again would be the 12th term.